So this is 1.1, section 1.1 in pre-calculus, the sets of numbers and the Cartesian coordinate system. So let's talk about some set terminology. So we refer to the empty set, that's the set with no elements in it, using this 0 here with a line through it, or curly brackets with no elements in the set. Then the natural numbers, or sometimes called the counting numbers, are just 1, 2, 3, 4, and on and on and on. Then the whole numbers, we put the 0 in there to the natural numbers, and you've got the set of whole numbers, all positive values. All right, that's the whole numbers. And then the integers, you add in the negative values as well as 0, and then you have the integers. Okay, the rational numbers, these are fractions. Fractions are ratios. So the rational numbers are ratios of integers. Okay, since we have negative numbers in the set of integers, we can also have negative rational numbers. Okay, so examples of rational numbers might be negative 2/3, 3/5, something like that. Another way to think about rational numbers is that they have a repeating or a terminating decimal representation. If you took any fraction and you divided, you would get a decimal number, which would be either a repeating decimal. Let's take an example, maybe 1.333 repeating. Well, that is also represented by 4/3. Okay, so those are rational numbers. They're the same number. Or you could have a terminating decimal, let's say 1.25, which would also be represented by 5/4. Okay, so those are rational numbers. And then we have the real numbers. Okay, so that's any number that has a decimal representation. And then the irrational numbers. So an irrational number is a decimal number which doesn't repeat or terminate. So it's almost like the opposite of a rational number. A rational number does either repeat or terminate, but an irrational number does neither of those two things. For example, pi. We know that pi is a famous irrational number, that it goes on and on and on. It never repeats the pattern of decimal numbers at the end. And then take, for instance, root 3 or root 7. If you type that into your calculator, you'll see that there's no organized or repetitive pattern to the decimal numbers, the numbers to the right of the decimal point. Okay, so those are irrational numbers. And then the big group, complex numbers, if you'll recall, the A is the real part, and the B is the imaginary part, where I is the square root of -1. So the real number set is actually a subset of the complex numbers, where this part over here is just zeroed out. In fact, B would be 0. Okay, so the real numbers, the entire set of real numbers, is just a subset of a larger set called the complex numbers. So let's classify these numbers here according to this list. So I've got for A, 256. So that's a whole number. That's an integer. It's a real number. It's a natural number. And it could also be considered a rational number because the fraction 256/1 is the ratio of two integers. Okay. And then we've got the square root of 7. Okay, the square root of 7 is an irrational number because if you find the decimal equivalent, you'll find that it neither terminates nor repeats. So that means it's not a whole number or an integer, but it is a real number. Okay, it's a real number, It has a decimal representation. It just doesn't have a terminal or repeating decimal portion of it. Okay, so it's those two things. And then we've got the number 3. Okay, so 3 is a whole number. It's an integer. It's a real number, natural number, and it's also a rational number because you could put a 1 underneath it. All right, so now we look at -8. So we've added a negative in there. Okay, so it's not a whole number then because the negative. It's an integer. It's a real number. It's not a natural number because of the negative. It is a rational number because it is the ratio of two integers. Okay, so then we got 0. It's definitely not irrational. It is a whole number. Whole number has set of whole numbers includes 0. It is an integer because you can make the ratio of integers 0/1. It is a real number. And C, it's not a counting number, so it's not a natural number. Let's see. Wait a minute now. Rational number. This means it's a rational number. All right. So what else? 1.5. So it's not irrational. It's not whole. Not an integer. It is real. It's not a natural. Well, let's see. Rational. It's a terminating decimal, so that makes it a rational. We also know that it's a ratio of the integers 3/2. All right. Then we've got 389.006. So that is a terminating decimal. So that definitely makes that rational. And it is real, but it's none of the other things. All right, so one more. 2/3. All right, so it's definitely not irrational, not whole, not an integer. It is real. It's not natural, and it is rational. The ratio of two integers. Now we're going to talk about this new thing called interval notation, which is a shortcut for using our curly bracket notation, our set builder notation that we used all the way through our SOL courses. Okay, now once we get to pre-calc and then calculus, we switch over to interval notation. Okay, so looking at this first here, curly brackets, set builder notation, this says x such that x is between a and b, but it does not include a and b in the set because there's no little line here under the equal. That's represented on the number line as an open dot here and here on both ends, and every point in between a and b is included in the set. The way we represent that in interval notation is smooth bracket represents empty circle. Smooth bracket represents empty circle. So we read this as the interval between a and b, not including a and b. Now here we've got a little line with the a. That means we have a filled in dot at the a. We have no little line here, open dot. But the filled in dot means we're going to use a square bracket for the a when you have this little equal sign. That means a is included in the set. This is the interval between a and b. A is included, b is not included. Over here, b is included, a is not. Square bracket for the b, filled in dot for the b, smooth bracket, empty circle. So this is the interval between a and b, where b is included, a is not. Here we've got a line both at the a and the b, so that means both a and b are included in the set, filled in dot on either end. This is interpret as the interval between A and B, where A and B are both included in the set. Okay, over here, we're talking about x such that x is less than b but does not include b. So b is not included, empty circle, but everything to the left is included. Now we call the arrowhead negative infinity or positive infinity. Okay, so that's what the arrowhead represents. Okay, so in this case here, we're going to say between the interval between negative infinity and b not included. Negative infinity is going to have a round bracket because negative infinity is just a concept. It's not an actual number. So in this one right here, you've got a little line, so we've got our square bracket and our filled in dot. So the interval between negative infinity and b, including b in the set. Here, x is greater than a is not included in the set, so a is empty to the right this time, greater than a. Okay, so we're going from the interval between a and infinity, where a is not included. Infinity always gets a round bracket. This one here says the x such that x is greater than or equal to a, so we got a filled in dotted a, greater than, so positive infinity to the right. So the interval such that a is included in the set, the interval between a and infinity. So this r represents all real numbers, so that means to the left, negative infinity, and to the right, positive infinity. So we represent that as smooth brackets on either side, negative infinity to positive infinity. This is all real numbers. Now, some symbols that we may or may not have seen before. So this is the intersection of A and B is represented by this upside down U. So this right here, this notation means the intersection of A and B. So if I have some set A that overlaps some set B, all right, so we've got some elements in the middle, and we've got elements in both set A and set B. The intersection of A and B is going to be the part that overlaps in the middle here. This part right here. That's your intersection. So there's two elements that are in that overlapping region, and that's called the intersection of set A and set B. All right. Then we've got the union. Let's get my skinny pencil here. The union of set A and B is represented by the U symbol like that. And so when we're talking about the union of set A and B, that means we join them both together and create a set that contains everything that's in A and everything that's in B. Both of them all together, joined together to form a new set. So we're going to express these sets of numbers using interval notation. So first I want to look at number 1 on a number line. So I've got a -2 and I've got a 2. So I've got a little line here on both of those numbers, so filled in dot. So that means x is less than or equal to -2, and it's greater than or equal to +2. So this is a two-piece number line right here, set representation, I should say. So we're going to use the union symbol. So we're going to say negative infinity to -2, square bracket, because it's filled in union symbol, square bracket, 2 to infinity, round bracket. Okay, so I've got a two-piece set there, and we use the union symbol for that. All right, number 2, I've got x such that x is not equal to 3, not equal to 3, but it is allowed to be anything to the left of 3, also includes anything to the right of 3. So I've also got two pieces, 1, 2, with a hole in the middle here, so I need the union symbol for that as well. So that's negative infinity to 3, this time round bracket, union 3 to infinity, round bracket, two pieces with a hole in the middle. So that's why these two numbers are the same here, because it's just a hole. Okay, it's not really a big gap like this. Alright, so now let's look at the third one. Alright, so it says x such that x is not equal to either negative 3, not equal, or not equal to 3. So it can be everything else. Let's get a different color here. So it can be over here, it could be in here, and it could be over here. Just can't be those two places. So we need two union symbols here because we've got a three-piece graph. So I've got negative infinity to negative 3, I've got negative 3 to 3, and then I've got 3 to infinity. All right, one more. I've got number 4, so I've got negative 1, 3, and 5. So x is between negative 1 and 3, not filled in at negative 1, filled in at 3, so 3 is included, negative 1 is not, and it's everything between there. Alright, and then it says it can equal 5, just a dot on 5, doesn't say anything else about this region here, so that's not included, nor is this, and also this is not included. Alright, so the way I'm going to write that, I'm going to say between negative 1 and 3, where 3 is included, and then I've also got just plain 5 included. Okay, next, symmetry about either the x-axis, the y-axis, or this is supposed to say origin here, it's got cut out somehow, origin. Alright, so we're talking about symmetry about the x-axis, we're talking about symmetry about this line here. Alright, so for instance, if I look at point P and I fold up along that x-axis red line, that P is going to wind up right on top of that S. Likewise, Q is going to wind up right on top of the R, because they have the same distance from that fold. Okay, so those are considered points that are symmetric about the x-axis. So if you're symmetric about the x-axis, your xy point and your x negative y point are 2 points that are symmetric about the x-axis. So in other words, your x value does not change, it's the same number. Your y value is the opposite of this value here. So if this is 3, this would be negative 3. Okay, so that's symmetry about the x-axis. Now if we're talking about symmetry about the y-axis, we're talking about this being the fold line now. So that means this dot has got to wind up on top of this dot when you fold on that line. Likewise, this dot is going to wind up on top of this dot when you fold on the line. So you can see that the x value, for instance, if this is 4, this would be negative 4. If this was 5, this would still be 5. Okay, so your x value, the sign changes. Your y value, exactly the same. Same down here. This is positive, this would be negative. This is negative y, same number, negative y. All right, one more. So if we're symmetric about the origin, here's the origin. So we're symmetric about a dot. So if you're symmetric about a dot, it's a rotational symmetry. So we can think about, let's take for instance this point here, x, y. All right? I'm going to rotate that dot 180 degrees about the origin, and it's going to wind up right on top of this dot here. Is going to wind up right on top of that dot. Okay? So I'm rotating this dot 180 degrees around the origin, winds up on that dot. That's what we call origin symmetry, symmetry about the origin. Okay? So if that's the case, then we could look at these other two dots here. Let's draw another line connecting them to the origin. So if I rotated this dot 180 degrees about the origin, would wind up on this dot. So Q and S are symmetric about the origin as well. Okay, so if you look at, this is the point XY, this point which is symmetric to it about the origin would be negative x, negative y. So if this was 3, 5, this would be negative 3, negative 5. Over here, if this was negative 3, 5, this one would be positive 3, negative 5. So if we've got the point negative 2, 3, that's point P, we want to find the point which is symmetric with respect to the x-axis. So that means it's going to go across, it's going to wind up right there. So that means you're going to have the same x value and the opposite y value. So negative 2, negative 3. And if you're symmetric about the y-axis, that means you're going to go over to here. So you're going to have the same y value, but the opposite x value. Okay, if you're symmetric about the origin, there's the origin, that means you're going to be over here. Okay, so I'm rotating this dot 180 degrees about the origin, going to wind up over here. Alright, so that's going to negate the x, it's going to become positive, it's going to negate the y, and that's going to become negative. Alright, okay. Next thing we're going to talk about is the distance between 2 points in the coordinate plane. Because we want to think about this as a right triangle. Alright. Okay, so remember we're in the xy plane. Alright, so if I'm talking about, let's see, this distance here, let's call that A, and we'll call this one over here, we'll call that B. So remember that Pythagorean theorem, I'm just going to abbreviate it, speed this video up a little, would say A squared plus B squared is equal to D squared. Alright, so A is your x1, okay, so this value right here is x1 minus x0. Right, so this is x1 minus x0. And then we have this squared. Alright, so then plus. Okay, so B would be the difference in the y values. Vertical distance. Vertical distance would be this y value, y1, minus this y value, y0. y1 minus y0 squared. Okay, so that's equal to d squared. Right, so if I just wanted to find d, I would take the square root of both sides. So let's put the d over here. So d is just this big radical right there, and that's considered the distance between the point P and the point Q. Now, you might remember this from geometry. It's this long formula here, which I don't usually like people to memorize and think of distance formula in terms of a memory type exercise. I want you to think about it in terms of Pythagorean theorem. All right, so let's try one. So if I'm given 2 points, point P and point Q, remember we're going to take the difference in the x's and square it. All right, so that would be in either order. So let's go -2 minus 1. So that's the difference in the x's. I'm going to square that. So remember that's this side over here. So we're going to square it. And then the difference in the y's, so that would be 3 minus -3. And we're going to square it. All right, so what we did there was we said -2 minus 1 squared, that's this side, plus 3 minus -3, that's this side, squared. And then we're going to take the square root of all that. It's going to be d. All right, so this is d. So that's -2 minus 1, that's -3 squared. And that's 3 minus -3, so that's 3 plus 3, so that's 6 squared. So that's 9 plus 36, so that's 45. All right, now we need to simplify when we can. So this is equal to 3 on the outside, 5 on the inside. Okay, so that's the distance, 3 root 5, between point P and point Q. So that's some decimal number somewhere between 6 and 7. And you know that because the square root of 36 is 6, square root of 49 is 7. And we can see that the square root of 45 is somewhere in the middle there, maybe closer to 7. All right, so that's a decimal number, that's a real number. Okay, the very last thing I'm going to talk about in 1.1 is midpoint. Okay, so midpoint is the point halfway between point P and Q here, the point XY, halfway between. So that means that this line segment is equivalent to this line segment. So we want to think about that. The easiest way to think about it is that you can average the x values, and that would become your x coordinate of the midpoint, and you can average your y values, and that would become the y coordinate of the midpoint. So then we would have a new point. So the average would be x0 plus x1, and the average of the y coordinates would be that. All right, and so that would be your midpoint xy. Some people talk about that as being the midpoint formula, but it's not really a formula. In my opinion, it's just the average of two x values and the average of two y values. All right, so let's do it. So we're going to average the x values. So we've got -2 plus 1 divided by 2. And then we're going to average the y values. So we've got 3 plus -3 divided by 2. Remember, when you take an average, you're adding the number of items in a list and dividing by the number of items in the list. So this would be your coordinate pair. So that's -1 over 2. That's 0 over 2. So your coordinate pair, your point is negative 1/2, 0. Let me just point out that it doesn't matter whether you have the 1 first and the negative 2 in the opposite order. Same here. It doesn't matter the order of a sum. You're still going to get the same answer. Okay, the very last problem. If I've got an A and a B, here's an A, here's a B, and then my midpoint is M. Those two pieces are the same size. It says the midpoint of AB is given as 4, 0. A is 3, 7. What is B? Unknown. We don't know B. Okay, but we do know that the average of 3 and X has to be 4. And we do know that the average of 7 and Y has to be 0. Alright, so we could solve these. So 3 plus X has got to be 8, so X must be 5. Alright, over here, same procedure. 7 plus Y, it's got to be 0, so Y must be negative 7. Okay, so the point XY is 5, negative 7.